Hello, can you hear me?
Yeah, I can hear you well.
Yeah, okay. I'm one of my desktop doesn't have a camera and a mic, so I'm just gonna have to present through two computers, but yeah.
Oh, okay, I see. So you're in the office now?
Yeah, that's correct. Yeah.
Okay, so let's wait for 1 or 2 minutes before we get started. Great to see everyone. So it has been a busy week and almost the end of the semester. So many of you might be quite busy with your final exams or final projects. So, but it's great that we can win before the end of the semester. So, so Charles is going to present this week, and in 2 weeks, Yi is going to make a different presentation that we are going to talk a little bit about after Charles' presentation. And then we'll have a break. We'll come back when the new semester starts. So you know keep tuned for future announcement regarding when we are going to meet. But I do believe that we should have a break because it's almost the Christmas New Year time, and some of you may plan traveling. Um, Others may hold parties and other celebrations. So we need to take a little bit time off to celebrate what we have achieved for 2023. Okay, so let's maybe wait for 1 more minute before we get started. And a lot of interesting things are happening worldwide regarding AI. So some of you may have heard listen to the recent panel discussions with Elon Musk and also the CEO of NVIDIA, and both predicted that within the next 3 to 5 years we'll have AGI, the super artificial intelligence that may surpass any human capacity. It's interesting that they tend to lay out a very imminent time framework compared to what the vice president of Microsoft, who predicts that the AGI would not be near, and he predicted in the next 50 years we probably have an AGI. Of course, no, there's no universal definition on what is AGI, um, and no, is up to different interpretations depending on how you define them. And people have dramatically different views. Right? So no, who knows, right? The technology is advancing so quickly, and now we have ChatGPT. We think, well, the machine is about at the human level of intelligence, and definitely more knowledgeable than any of us in this planet. But this probably would be just the very beginning. And what would happen, right, if we have super artificial intelligence that surpasses any one of us? What's our human value if we have this super intelligence, right? What are the roles? We will all be replaced by AI. It is a doomsday argument, or it is a happy ending story that we can all relax and stay on our couch and just watch the wonderful entertainment produced by AI, right? Who knows? Okay, so I think we should get started. So for this talk, Charles is very generous in initiating this topic. And this topic definitely is state of the art and very much pertaining to his dissertation. So today he's going to introduce several innovative approaches to do fine tuning of the large language models. As many of you know, nowadays we can't really train our own large language models because it's too expensive, right? Computational wise, time wise, that we simply don't have the resources to train our own model. On the other hand, fine-tuning those large models when those large models become larger and larger becomes such a burdensome and also potentially expensive business. So to address those fine-tuning issues, Charles was reading a lot of interesting articles regarding how we can sufficiently and efficiently train those large language models at scale, but also avoid computational barrier and try to do that as efficiently as possible. So without further ado, let's welcome Charles to give us his presentation.
Okay, thank you very much. Can you guys see the screen? And
yes.
Yeah, okay, awesome. I'm gonna speak from a different computer and I'm gonna present in a different computer, so forgive me for that. But yeah, let's get started. So today I'll be presenting parameter efficient fine-tuning, right? So this will kind of be my talk. I'll first go through what fine-tuning is. I'll go through some in-context learning alternatives, and then I would define parameter efficient fine-tuning. I would go through in this order: prefix tuning, prompt tuning, p-tuning, LoRa, and IA3. Yeah, I do apologize. The slide is a bit off. I just tried to upload it in Google Slides, but yeah. So really, right? So firstly, right? Okay, so in the world of large language models or any deep learning, or in fact any machine learning algorithm, right? When you fine tune, right, you have your pre-trained model weights, right? And then basically what happens is that you have you feed this your own data, and you basically try and change the weights, right? You go into the model and you try to change the entire model's architectures and its weights, right? And then you update the weights accordingly, right? Based on how many epochs you have, right? So the problem with this in large language models, right, is that you can see, right, even in GPT-1 all the way to GPT-3, it gets bigger and bigger, right? So you essentially now have to, fine-tune all these billions of parameters. At some point, it just no longer becomes practical anymore, right? And unless you have GPUs, which aren't cheap, right? You just can't do it, right? And in essence, you're actually the computational power needed is twice the amount of parameters in essence, right? Because at one given point of time, you need to actually have the change in weights, right? And you also need to have the original weights itself, which you add to the change in weights, right? So these two here, right? So it becomes very computationally intensive, right? So other problems, right, is that you need typically when we do this, right, we have one set of downstream task, right? Sentiment analysis, for example, of a certain text, tweets, for example, right? Maybe you have another set of tasks that you want, like you want to compare the similarity of two texts, for example. So you always have to keep on doing this for a single domain, right? So it just becomes more and more computationally intensive, right? You also need abundant and representative data, right? And data labeling can be very, very expensive, right? So that's another problem with fine-tuning. And another problem which I didn't fit in here is that it could overfit, right? And sometimes you don't know, right? It could easily overfit in itself, right? So some people have come out, not some people, but a very good alternative would be in-context learning, right? Where in essence, you feed it prompts, right? You prompt the large language model and you guide the large language model into thinking a certain way, right? So this is a very good example, right, of what we call four-shot prompt, right? So for example, you feed this into the large language model, right? So please unscramble the letters into a word and write that word, right? And I give it 4 examples. This is casino, this is froggy, this is simple, and this is biggest. Now, And then I ask large language model, now can you do this for me, right? You are trying to prompt large language model to think a certain way so it could answer the question. I know it's at night, but does anybody want to give a guess on what the answer to this is?
This is pretty hard.
Yeah, but you know, large language models managed to do this with just 4 prompts. So
someone roasted. Oh yeah.
Yeah. All right. I mean, but that's the power of large language models, right? You see, even us, it took us a while to do it. They do it in four prompts. So yeah, in 4 shots. So yeah, so that's an example of in-context learning, right? But even that has so it has advantages, right? You can perform many tasks immediately without fine-tuning. It allows for mixed batches as well, right? You can do it across many tasks and different batches of different data, right? But of course, it still has it has its own limitations, right? This paper found that sometimes if you just swap the shots, for example, right, you can sometimes get a very different probability as to what the answer would be, right? So it is very it can, you know, it really begs the question, right? Is the large language model learning correctly from these shots, right? And they even did show examples whereby sometimes it just gives a different answer just simply by swapping the order. Right. Another thing is that the longer your prompts are, right, the more expensive, the more memory it consumes, right? Especially for models like GPT-4, where you basically it's purchased at a per token basis, right? And at some point also, right, you are limited by the amount of token inputs, right? So it's just not feasible again, right? That brings about limitations and it's not feasible, right? So now, welcome to the world of parameter efficient fine-tuning, right? Where basically, in some sense, it tries to, it's in some sense in the middle of both, right? So of course, parameter efficient fine-tuning is a terminology that, you know, has been thrown around quite frequently. And you know, many people have many definitions. Sadly, unfortunately, most people will have their own definition when they write their own paper on parameter efficient fine-tuning. So it kind of fits their own definition, or they kind of say, hey, you know, this other people who did it in the past, they don't really fit this definition, you know, we do fit it. But I'm just going to show a few examples, right? So for example, Li and Liang, they said that it's lightweight fine-tuning. It freezes most of the pre-trained parameters and modifies the pre-trained model with small trainable modules. And the goal is to identify high-performing architectures, right, of the models and the subset of pre-trained models, pre-trained parameters to tune, right? This other set of authors give another definition. It provides a strong performance on any task without manual tuning or per task adjustments, and it's a realistic option in few short settings when limited data is available. Right, but in essence, right, what essentially it is that you basically create tricks, and I'll explain some of these tricks later, that will allow the model, right, to be tuned by adjusting only a small amount of parameters. So instead of going to the model's architecture, like I showed earlier, and adjusting every single weight, right, such that at the end of the day, you have this model which is fine-tuned to your own task, right? But it requires a lot of computational power, right? You eventually just explore a few tricks such that you are only adjusting a small amount of parameters while you keep everything else frozen, right? So you keep the model's weights frozen and you adjust only a small amount of parameters. So the first one that I'll be introducing is prefix tuning. And the reason why I'll introduce it in this order is because, you know, prefix tuning was the one that kind of started it all. And of course, people would try to benchmark themselves in each of these methods. So yeah, all right. So this is the paper prefix tuning that started it all. So as you can see, right, as you can see from the top here, right, in fine tuning, you have the entire model, right? So here the task is, you know, convert this, right? Convert table to text, basically convert Starbucks type coffee shop, convert it to Starbucks serves coffee, for example, right? So in traditional fine-tuning, you would fine-tune the entire architecture, right? But in prefix tuning, right? You keep everything frozen, right? Instead, you have you insert prefixes here. And what prefixes are basically they are like invisible virtual tokens, right? So they represent nothing. They're just virtual. You just put them in there, right? And you just tell the model, hey, tune these virtual and invisible tokens for me while you freeze everything else, right? So how do you tune it, right? It's very simple. So as you can see, here is the prefix, right? This is what a GPT-2 model would look like, right? Here is the prefix, right? So here is the X, right? Which is the input, Harry Potter, education Hogwarts. And you're telling the model to make this into a sentence. So this is the output, Harry Potter is graduated from Hogwarts, right? I mean, it's still wrong. I don't know why they put this in the paper, but anyways, you have the prefix here, right? As you can see, it's invisible. It's just virtual tokens, right? And this basically has a dimension of this PIDX here represents the length of the prefix, and it has the same dimension as the activation of everything else, right? So you basically fit or you squeeze and you force in this case a prefix of length of 2, you force them into the start of your model, right? And basically what happens is that in order to do that, right, before that you have sorry, if you can see below here, you basically have a even smaller prefix, right? So it has this is the length of the prefix times k, right, where k is smaller than the length of the dimension here. You pass it through a multi-layer perceptron model, which is basically a neural network, and it upscales it, right, to contain the same number of dimensions, right, as these activation functions here. And you feed these activation functions into the model, right, at the start of the model. You prepend it at the start of the input itself, right? So the goal now is you end up adjusting this, right? You adjust this this set of prefixes over here, right? So and the same goes for an encoder decoder model, right? Which basically, so encoder decoder model is when you have encoder and decoders instead of just like GPT, right? Where it's just a set of decoders, right? So encoder decoder model is the same. You just insert prefixes at the start before the input and at the decoder as well at the start before the output, right? And what's the ideal prefix length? So they did a few experiments and they found that in table to text, right, 10 is the ideal prefix length. And for tasks like summarization, 100 is the ideal prefix length, right? And then they claim
so Charles, I have a question here. Maybe so my understanding of this prefix works like a scalar, right? It means that when the model is going into the fine-tuning process, the x and y, the representations will stay the same, and you are only fine-tuning, basically figuring out the optimal values for example, here in the decoder model, H1 and H2, which are the parameters in the prefix. So prefix work very much like a scalar of the entire, this giant vector. Is that a fair understanding?
that is a very good understanding of it. Yes, that's correct. Yep.
Okay,
So,
thank you.
yeah, so you're only fine-tuning this portion here. If you my mouse, you're only fine-tuning this portion here, which is even smaller than actually H. You're not directly fine-tuning H1 and H2, which is represented by P here, but actually you're fine-tuning an even smaller one here.
Oh, okay, gotcha. Yeah, this is fantastic. Yeah.
Yeah. And later I'll show you how many. So yeah, and they claim that at least for most of the cases, right, in benchmark data sets, as you can see, prefix tuning outperforms fine-tuning, right, in most cases, right, through benchmark models, right? And then they also showed that fine-tuning is blue here, that prefix tuning performs well, or even better than fine tuning, when you have limited training data sizes, right? So now I'm going to show you how to implement it in code, right? So of course, the first thing, it's very simple actually. If you know how to do normal fine tuning, this is a walk in the park for you, right? So the first thing you have to do is just import the PEFT function, which is parameter efficient fine tuning, right? You have to make sure you install it into your system. You have prefix tuning here, right? And then, so for today's task, I'll use a real life data set, right? I basically got this data set. Let me just show you. Right, so it's 3,613, right? It has a text and it has labels, right, of emotion. So joy, anger, sadness, and fear. Joy, anger, sadness, and fear, and I think surprise is the last one. There are four labels in total, right? Joy, anger, sadness, fear, anger, fear, sadness, and joy. So just 4, right? And we are gonna test it. I'm gonna show you in real life how fast and efficient it is, right? So the training size has 3,613 samples, right? Like any large language model, this class just simply prepares the data set. You do it like how you would do it when you're fine tuning itself. So now we prepare the prefix tuning configurations, right? So you define the amount, the prefix tuning here. You say, you tell the PEFT package you're hoping to do prefix tuning. Of course, you define your model, right? And remember, just now I talked about the dead tokens, the virtual tokens that we insert at the start of the model itself, and those are the only ones that will be tuned, right? The rest will be frozen. So here you have to specify the number of tokens you want. So I'm specifying 10 simply because, right, they tell me to, right, in the paper. Right, so you do that. Have I run this? I hope I've run this already. Okay, you do this, right? And then the same, right? You just define your large language model, you define your tokenizer, right? You run it on your data set, you define your model as a sequence classification, right? So that's what I'll do. And then you could see, right, you can print this out, right? So you get the PEFT model, you define your model here, right? So here you have to make sure that the model, right, after you define your large language model, right, you wrap it around this PEFT model function, right? And you make sure you tell them, right, that this is my configuration, my parameter efficient fine tuning configuration, and this is the model of which I want to fine tune it with, right? And as you can see here, right, this model has 125 million parameters, right? But I'm only fine tuning 777,000 parameters, or 0.62% of it. So it's very impressive, right? And right, so I run this, okay, now. Right, and then you define the optimizer because you want to optimize those prefixes, right? And you fine tune it, right? Usually if it's fine tuning, nobody's model doesn't support. Okay. Right, usually if it's fine tuning, yeah, it's not, we're not going to show it, but right, because it's prefix tuning and it's parameter efficient, right? So we're going to show it here. So as you can see, right, we have defined it earlier here for just 4 epochs. Most of them would recommend more, but just for demonstration purposes, right, I would show 4 epochs, right? And you can see how fast it is. This is 1 epoch now. And it's basically going to finish within less than a minute, right? So let's just wait for it.
I have a question.
Yes, go on.
One, how can this like prefix finding choose the training parameters? Is that choose automatically, or it's only choose like the prefix, or it's add some more other?
Yeah, that's a good question. So as you can see here, only the prefixes are fine-tuned. These are the only ones that are fine-tuned. Nothing else is fine-tuned. So you can see here, only this P here, this prefix here, only that's fine-tuned. The rest of the model is frozen. It does not change at all during fine-tuning. So does that answer your question?
So like in this picture, the prefix is space. It's empty.
Yes, it's meant to be empty because they're virtual tokens. So in front of the model, right, you just insert a virtual date token. It's a date token. So it's an empty token, right? You randomly initialize them, right? And then you're telling the model to fine-tune this for you.
Right. So if I understand correctly, you basically, for example, if your previous vector length is say 10, right? And then you add 2 more tokens, so that's 12. And the 10 tokens stay fixed. And you randomize, you provide random numbers to this additional 2 tokens on the prefix. And then you just train the model, fine-tune the model on those 2 additional parameters, right? To find the optimal value of this H1 and H2. As simple as that.
Yes, that's correct. Yes.
This is really, really interesting.
Yeah.
So especially I'm kind of I find really impressive, when you show that this kind of parameter efficient fine-tuning have a higher accuracy compared to fine-tuning. So I guess that resonated with me because you have limited data, so that your original model is overfitting, right? So in this case, the data are not enough actually to allow you to find better parameter values for your model, because the model parameters are a lot more than the training data. In this case, if you fit a smaller number of parameters, maybe you get better results, right? So it's great if they have papers to show that when they increase the number of training data, the differences between the parameter efficient fine-tuning and the whole scale fine-tuning are going to diminish. And then later on, at some critical point, the fine-tuning become more preferable compared to the efficient parameter efficient fine-tuning.
Yeah.
Do you have a graph like that?
Yeah, actually this does it. As you can see, as the data size increases, more or less the fine-tuning catches up with parameter efficient fine-tuning.
Right.
I do not show it here, but they also did show in ablation studies within the paper that parameter efficient fine-tuning is best performed when you have limited data,
right?
Compared to actual fine-tuning, and they did show that indeed for very large data sets, actually fine-tuning, I mean, so this is how they phrase it in the paper. They said that fine-tuning our parameter efficient fine-tuning is slightly below fine-tuning, but you save a lot of time and computational resources.
That's right. That's
Yeah,
right.
that's how they, of course, they're not gonna publish a paper saying that, hey, it's lousy, but that's how they try to phrase it,
Right. They want to sell this idea. I think it makes sense, but if it would be better if they report the crossover point in which the fine-tuning become indifferent compared to parameter efficient fine-tuning.
Yep.
So we know exactly, as a rough idea, how much data that allow us to really leverage the power of parameter efficient fine-tuning.
That is correct. Yeah.
So yeah, if we know that, do we need 50,000 or do we need 5,000, right? So that is probably an important data point we want to know.
Yeah, that's correct. It would be nice to know that. But yeah, I mean, moving on, you can see, right, within less than 4 minutes, I already have my fine-tuned model, right? And it's pretty good, right, in terms of F1 score and accuracy. right? Whereas if I were to do it in fine tuning, 4 epochs, no way it's gonna happen. No way. You probably have to wait. That's all we'll be doing. We'll be staring at the screen, waiting for it to fine tune, right? So yeah, so that's the power of prefix tuning. Any questions on prefix tuning before I move on to the next method? Okay, none. So essentially, you can think about. I mean, we're all obesity. I think we're here because we're affiliated with Professor An in some sense, right? So we're all obesity researchers, right? You can think about it this way, right? You have a supermarket and somebody tells you, you know, your supermarket has been selling a lot of unhealthy food. I want you to change it, right? So fine tuning is when you go into the supermarket and you rearrange everything, right? And then you rearrange everything. Whereas prefix tuning, right? You know, you're essentially just saying, hey, you know, I have a bit of this space at the front, right? Maybe I should, at the front of the store, maybe I should just sell vegetables here at discounted prices, for example, or set up a booth, right, where I promote healthy eating, right? So that when my customers come in, right, you know, they'll still have the same food at the back, right, of the shop, but you know, when they come in, right, they will now be prompted, right, to basically purchase healthy foods, right? And that's what prefix tuning essentially is, right? So I'll move on now to prompt tuning. And I know this term has been used a lot, prompt tuning, but I would do it in the context of parameter efficient fine tuning, right? So it comes from this paper, if any of you are curious to read it, right? So it's essentially the same as prefix tuning, right? It's the same idea, but this time, right, they experimented with 3 ways, right, to get these tokens, right? The first one is random uniform, which is kind of what we did earlier. We train from scratch using random initialization, right? Sample vocab, right? So we take the initial prompt tokens, right? We draw it from the model's vocabulary, right? So you have the model, for example, like a bird, and you have its vocabulary, and you just randomly sample them from the vocabulary, right? And the third option, right, is you take the tokens, right, from the output classes itself. So for example, in our case, the output class is joy, sadness, or fear, right? We just take the tokens from the class label itself, right? So now the question is, which one is the best strategy, right? So they realized that random uniform is the worst, but sample vocab and class labeling is the best, more or less tied together, right? And they also they say, okay, what's the right prompt size at the front? And they found that around 20 is the best, right? Too large is not too good, and a size like 1 is just not practical itself, right? So
here, you know, if you go back to the previous slide, yeah, the previous one, yeah, this one, the class label. So if you add a token size of 20, and then you just repeat the label if the label is less than 20 tokens, is that what they implement?
So the real answer is I don't know. And for some reason, the package only gives these 2 options, random uniform and sample vocab.
Oh, okay.
Yeah, I don't know why they don't give class label as an option. But yeah, I mean, the real answer is I don't know.
Right, right. The first 2 are probably easier to understand. The third one is interesting. So for example, if you classify apple, right, the apple orange, just repeat apple like 5 times to get the 20 token. Yeah, so it's interesting how they think about the class label, and whether that, I would say, I don't know. I haven't really wrapped my mind around it, but I think do we need to consider cheating in this case, because it provide a label, and label is part of the embedding to predict itself. But of course, they initiate, right, the label. The final output will be labeled, but won't you actually leak information to the embedding? I don't know. You know, I haven't really seen this implemented. So, but I was kind of curious. Yeah, later on, if you have time, you could probably dig a little bit more into that to see how they really deal with this class label.
Yeah, that's an interesting point. I mean, I don't have the paper with me, but they did explain their intuition inside the paper. I just cannot remember off the fly, but yeah. But yeah, so basically, again, right? So model here is fine tuning and prompt tuning here. So they also ran experiments and they found that, right, in what 4 out of 6 of the experiments they run, right, their method was better than just naive fine tuning, right? So again, I would go back here and then I would show you the code, right? So the same, everything is the same, right? You import your package. Let me just to save some GPUs. You import the package, right? Again, just read data. This is how the data looks like. You prepare the data set, right? And then here, you need to initialize a prompt tuning text, right? Initialize the prompt tuning text. And of course, you don't forget to tell the PEFT package that you're performing prompt tuning, right? Again, I'm just choosing 20 tokens because that's what the paper recommended, 20 tokens. And then this is a bit misleading, but yeah, so prompt tuning initialization, right? You can choose, like I said, you can choose between text or random. For some reason, label is not an option. I don't know why, but so I'm just going to choose text, right? Which randomly selects tokens from the model's vocabulary itself, right? Which is why you have to specify the model here. So in this case, I'm using a version of Roberta. So they're gonna sample some text from the Roberta model, right? If I run this already, all right. And then again, just the same as previously, right? And then now you can see, right? The model has 125 million parameters. I'm only fine-tuning 609,000 parameters, right? So only 0.48% of the total parameters, right? Again, define the optimizer, and then we fine-tune, right? And you can see how fast it is, right? Just a few seconds. And all right, so we are running it for 4 epochs. And as you can see, the performance just improves, right? So now it's 78%. And hopefully we can reach 80%. Okay, 80%, but still, right? But you can see how fast it is, right? It's really fast, right? So yeah. Any questions?
Well, I guess not everyone is amazed. Now, everyone who has been doing large language model fine-tuning would be really lucky to see the efficiency of those fine-tuning methods, right? Usually we need to wait for hours, and still sometimes the program run into problem and the process stopped, right? We all experience that a lot. And to the fine-tuning method, I would say there's a lightning speed. So any of you probably have struggled with fine-tuning would agree with this. Yeah, I saw that EE raises. That's capitalized yes.
Yeah, okay. So yeah, I mean, yeah, but that's how great it is, right? So yeah, any questions on prompt tuning before I move on to the next method, P-tuning? Okay, none? All right. So P-tuning is from this paper, GPT Understands 2, right? It's the same. Again, it's the same, right? But the difference now is that, right? So we have pseudo prompts here, right? We have pseudo prompts that are inserted, right, into the model, right? But the difference now is that we have this prompt encoder here. So this prompt encoder, right, at least the authors, what they tried was they experimented with multi-layer perceptrons, LSTMs, and identity mapping. So identity mapping is just, you just map these pseudo prompts to the actual prompts, right? LSTM is long short-term memory, and multi-layer perceptron is just the neural networks, right? So essentially that's what P-tuning is, right? It's the same concept, but they basically have this prompt encoder inserted here, right? So you can kind of see the flow here, right? It started off with prefix tuning, someone came up with prompt tuning, and then now somebody tried to improve it with P-tuning, right? So which one is the best, right? Amongst the multi-layer perceptron, LSTM, or identity mapping. And they found that, either LSTM or multi-layer perceptrons work the best, right, in achieving the performances, right, in achieving the best performances, right? And then again, they tried P-tuning with full fine-tuning and PET here, which means just prompt tuning, right? And they showed, right, that in most cases, right, they achieve better performances, right? In most of them were done in the glue dataset, but across many benchmark datasets. Right? So again, we would go to P-tuning here, right? And then again, right, same, just import the packages, right? Read the data, right? You prepare the data set itself, right? And then for here, again, the same, right? Number of virtual tokens, right? Encoder reparameterization type is basically what I was talking about earlier, where, right, what do you want your prompt encoder to be, right? Do you want it to be a LSTM? Do you want it to be a multi-layer perceptron? So for this one, I choose multi-layer perceptron, right? And the encoder hidden size is basically the hidden state, right? In the hidden size of, so of course, in your neural network, right, you have to choose how many layer, what's the size, right, of your hidden state. So for this one, I just choose 128. You can fine tune it and you can increase it or you can decrease it. It's up to you, right? So again, that's all you need to know for the configurations, right?
So Charles, so I have a question here. So when you talk about, say, the MLP, so the MLP model, you initiate the, say, a model with all the parameters randomly initiated, right? And then you include the parameters of the MLP as part of the prompt into the larger language model. Is that what you mean?
Yes, that's correct. So the pseudo prompts are fed into this multi-layer perceptron.
Mm-hmm.
They are used to generate what is essentially, so you have these pseudo prompts and the outputs of these pseudo prompts that go into the multi-layer perceptron are fed into the model. So now the goal is to try and optimize the multi-layer perceptron. That's the answer.
Okay, so so basically, this would add on the top of the entire model, right? Not into every layer of the language model.
Yes, on top of the model.
Yeah, on top. Okay, so basically you have a MLP at the beginning, and then the output of the MLP would add in additional prompts and feed into the pre-trained language model, and the entire language model is frozen.
That is correct. Yes.
Okay. Yeah. Right.
So so again, we do it the same, and then so we have slightly more trainable parameters, right? Mainly because we now have the multi-layer perceptron, but still, right, it's 0.65% compared to so if we do fine-tuning, we have to fine-tune 125 million parameters, but this one we can just train 800,000, right, which is 0.65% of it's more, but still, it's very small, right? So again, and then we can define the optimizer, and then we fine tune, right? And
so Charles, could you go back to the model architecture, so you can take a look of the no, it's if you go to the model architecture, print the model and so we can take a look of what the model looks like. Position embedding. Well, actually, it doesn't really show. Probably doesn't show the MLP part.
That's correct.
It doesn't really show. Yeah, it's still the Roberta model itself. Yeah. Okay.
Yeah. So, unfortunately, But okay, so you can see it. So it's fast, right? We finished it in a few seconds, right? Does not perform as well as prompt tuning, but still, right? We managed to finish it so fast, right? Within 5-6 seconds for each epoch, right? So again, this is the power of parameter efficient fine tuning, right? So any questions before we move on to LoRa?
Do we have a comparison between the three of them, like the prefix, prompt, and p-tuning? Which one usually give a better performance compared to others?
So I mean, that's also one very frustrating thing that at least when I was reading these papers, that the short answer is no. And if they ever do, it's only because they outperform each other, right? So, I mean, I guess that's how it works, right? They're not going to say we perform worse than let's say, if I publish p-tuning, I'm not going to say I perform worse than prompt tuning, right? But if I perform better than prefix tuning, I'm gonna write those results down. So the short answer is no.
Right. Yeah, I guess so. Right.
In a very frustrating manner, the answer is no. Yeah.
That's right. And yeah, for a lot of time, it's just I mean, because it's data driven, right? So we don't really know for sure which one outperform the others, unless we do the huge number of experiments. It's really up to you to figure out by doing experiments. But the good news is it's very efficient. It takes minutes, not hours, not days to do those experiments. Because we are really in the domain of efficient fine tuning. My intuition may not be right. My intuition would be the p-tuning probably is inferior compared to prefix and prompt fine tuning, because the architecture is you have this, no matter what model is, it's LLP or MLP or LSTM, is stacked on top of the entire language model, so that it doesn't really capture the finer changes within the language model, whereas the other two tend to co-vary within the language model. So it at least it makes more resonance to me for the prefix and the prompt, but not so much about p-tuning.
I mean, I think that's
anyway, yeah.
I think that's what we're also getting here, because here we see we hit 78% accuracy, 77%, 77%, but we didn't do very well for p-tuning, right? So I'm guessing, yeah, that's the case. But
yeah, who knows, right? We have some intuition, but we not be right.
Yeah, and they're not gonna, most of the results they publish, as you can see here, you see they only compare themselves when they perform better, right? They're not gonna publish a result saying that we perform worse, right? So I mean, I guess that's the downside to it. But yeah. So far we've talked about these three methods. LoRa, in some sense, kind of changed everything, because so far what we did was that we just inserted, prompts, or we inserted virtual tokens at the front of every model, and we asked the model to optimize these tokens, right? So LoRa completely changes the game, right? It was published by Microsoft, I think, but it's basically called Low Rank Adoption of Large Language Models, right? So basically, they basically took this idea from this paper, right? And so basically, it shows that, large language models have low intrinsic dimension. So basically what happens is that you have large language models, you have all these tunable parameters, changeable weights, right? Let's say, for example, it's 100 by 100, right? Sure, in theory, you have a 100 by 100 matrix that you have to change the parameters of. But in essence, you can capture that information with a much smaller matrix, with a 50 by 50, for example, or 30 by 30, right? And most of the time, right, the change in weights are pretty consistent across the entire matrix, right? And that's the reason why you can capture it within a smaller matrix in itself. So they went a bit further by trying to show that, sure, we have low intrinsic dimension, but what about low intrinsic rank, right? So basically, low intrinsic rank is the idea that, right, aside from just having a matrix that's really large, 100 by 100, and you can represent them in, let's say, 50 by 50 or 30 by 30, right, that the matrix in itself, right, from the change in the weights, right, you basically could represent them as, there is some pattern to it, and you can represent them as some form of a linear combination in itself, right? So you can represent them as a linear combination in itself. So when you think, if you're a mathematician, you think linear combination, large matrix, right? So the first thing you do is you think, okay, let me have two matrices, and I just multiply them by together, right? So as you can see from the diagram here, you have the pre-trained weights. It's a D by K matrix, right? What they essentially did was that they have two matrices, right? D times R times K. If you multiply them together, you end up with the same thing, D times K. The reason why this is possible is because, like I said, right, they claim they're trying to prove that large language models have low intrinsic rank, right? Which you can represent them as a form of a linear combination, right? So in essence, because now you have two matrices, you're just multiplying them, right? You're multiplying them accordingly. So you're basically, each matrix within the D times K is represented by some linear combination, right, of a D times R times K matrix. So this matrix here, R times K, right, is A. They initialize them using a Gaussian processes or normal distribution, right, centered at 0. And B is simply initialized as 0, right? And this is very important, right? The R must be much, much, much smaller than the minimum dimension size of D times K in order for it to be parameter efficient, right? So now you have the change in weights here represented. This alpha is just a scaling factor. Alpha times A times B, right? This A times B is this 2, which you multiply it, and now you end up with the same weights, right? The same size as that of the pre-trained weights, right? So basically, yeah, there's just that, right? Your change in your W, which initially was D times K, is now represented by two very, very, very small, two much smaller matrices, right? So that's basically the whole idea, right? And again, they showed that LoRa is more efficient than fine-tuning, right? So the question now is, what is the right R, right? And to which weights should we apply it to, right? So they showed that R of 4 is basically sufficient, right? Which is definitely much smaller than the original dimension of the weights, and basically WQ here and WV here is the query and the value, right? So basically in actually, let me just show this. I'm just going to skip a bit, but basically this is how any large language model looks like, right? What makes a large language model, and we're talking about transformer-based models, right? What makes them very powerful and efficient is that it can understand context, right? So how does it understand context? It basically assigns attention to a sentence. So you have attention sentence called, let's say, for example, I don't know, I love pepperoni on pizza, for example, right? So pepperoni and pizza are probably more similar to each other compared to the rest of the sentence, right? So basically this QVK, key value query matrix, which is basically a softmax function of the query and the value. Actually, this is wrong, but the query and the key times the value, right? Right, it's basically multiplied with each the words are multiplied with each other through this equation to assign attention to each other, right? So basically they were thinking, okay, which of these should we apply them to, right? Should we apply them to every single query key and value? Should we apply them to the entire model? And they showed that just having the query and the value, just applying them to the query and the value, applying this method to the query and the value is already sufficient, right, to achieve good performances, right, in the LoRa model itself, right? So, and again, this time they managed to show how much VRAM consumption you eventually would save. So for GPT-3, the largest GPT-3, 175 billion parameters, right, they showed that initially you only, if you use fine-tuning, you need 1.2 terabytes of VRAMs, right? That would cost, I don't know, millions or billions of dollars, right? But now, okay, I mean, it's still a lot, but they showed that, okay, with our LoRa, you only need 350 gigabytes, right? And 25% of speed up time as well. So yeah, essentially, and LoRa was basically made, sure, I mean, it's, of course, you can always try limited data, but it's really made to really ensure that, it's made with the goal of allowing people to fine-tune a large model with much limited resources, right? So now let's go to LoRa. And then again, it's the same concept. Let me just restart this so I could free up my RAM. Okay, yeah, so again, just import the functions, read the files. Oops.
So Charles, one question about the matrix decomposition. I think it's really a brilliant idea that they decompose the huge matrix into actually two different matrices, right? And they set. So I'm not really quite understand how they set the B to be 0, or the B won't be entirely 0, right? It would be like a much reduced size of the matrix. Most of the values were set to 0 if they are very small, but they still need to keep some values to be non-zero, because otherwise, if the B is entirely zeros, then a 0 matrix time anything would be just a 0 matrix, right? So in that case, how they are going to estimate the parameters in R?
So I mean, B is just the initialized value. So they initialize B as 0.
Oh, initialize B as 0.
Yeah,
oh, okay,
yeah.
I
So
see.
B is
I
not
see.
0. Yeah, yeah. So at the very start, it's all zeros, but of course, as you fine tune it, it changes. Yep.
Oh, okay.
And
Okay.
the same for A. It starts off with this normal distribution centered around 0. Yeah. And of course, the numbers would change over time. But yeah.
Right. Okay. Okay. So it's interesting how they think about how they thought of this, right? The B initially is all 0, but A follows a standard normal distribution.
That is
And then, but mainly the task is to figure out the parameters in the three matrices, right? The B and A and the R for both the value matrix and the key matrix, if I remember clearly.
Yeah, just B and A. R is just basically the size of.
Oh, R is just the size. Oh, okay.
Yeah,
Okay.
yeah,
Just
yeah.
B and figure out B and value B and A.
Yes, that's
But
correct.
okay.
So
But B and A in together, they are much smaller in terms of number of parameters compared to the pre-trained matrix weights.
that is correct. So, and that's controlled by the R here, where the R is much smaller than dimension of, so the D and the K of the weights itself. Yeah.
Okay. Okay.
Yeah,
Yeah, that's a very interesting idea.
Yeah,
Okay.
and this is when R, the number, the size of your matrix, right? They recommend somewhere around 4, 2 or 4. But yeah.
Okay, so this is very small compared to the
Yes,
existing matrix.
that is correct. Yeah. So again, we do the same, right? And then we define the prefix configurations. You want to print out your model here. And the reason why I do that is because remember earlier, I mentioned that, right? Over here, you could choose, right, which weights you want to apply this LoRa method to, right? So we will want to choose between where we want to apply them to, right? And I just take the example given here where they recommended, or I read, as someone who's read the paper, I would just take their recommendations, right, which is to apply it to the query and the value weights, right? So that's what I'm going to do here. So you print them out, and then they're called query and value. So I'm just going to insert them here. So that's when target modules come in, right? So you define query and the value, and then R here is the size of the matrix, right? And then they recommend around 4. So, okay, I'm going to change this to 4. They recommend 4, right? LoRa alpha, right, is basically the alpha here, right? It's just a scaling factor. So, right, I'm just going to take the default value of 16, and when the dropout is basically the dropout rate during the fine-tuning itself, right? Because they're fine-tuning these two matrices. So these are my parameters. Of course, you define your learning rate, right? And then again, right, now we see, as usual, right, we only have to train 0.59% of all the parameters, right? Instead of training 125 million, right, we only train 0.59%. And bear in mind, this is decided by the R that you choose here, right? So the smaller the R, the less parameters you have to tune. So this is decided by the R, again, the optimizer, and then now we fine tune it, right? And you can see how fast it is again, right? Just a few seconds, and then there we have it, right? And it's already performing very well, 78% at the very start. So let's just give it a few more seconds. Now you see, now we've reached 84% with LoRa. And okay, so now it dropped a bit, but you can see we achieve really good performances in very, very short amount of time, right? Just by, and it's really just a very simple trick, right? You know, you're just basically taking a pre-trained weights and, you know, you're just dividing it into two separate matrices, right? And yeah, and there you have it, right? So any questions before we move on?
Yeah.
Yeah, go ahead.
Is that the matrix, you mean like you choose matrix equals to 4, the 4, that means that each layer you only like fine-tuned 4 parameters at each layer?
No. No, you are basically fine-tuning D times R times K, right? And you're basically having this D times K matrix, right? Which is very large, right? Let's say 100 by 100, right? Let's say D is equal to 100, K is equal to 100. Now you're just basically in full fine-tuning, you fine-tune the entire thing, right? 100 by 100, right? But with a D time, with this trick, you're basically fine-tuning 100 times 4 and 4 times 100.
So like usually you'll fine-tune like 100 times 100, it's 10,000, but this for LoRa you only train 800.
That is correct. Yes, okay. That is correct. So, and this 800, is it 800? Right, it's
4 times 100.
100 times 4 times 4 times 100. So what, 800? Yeah, 800, that's correct. Yes, 800. Yes. So yes, that is correct. Yeah, you're basically, yeah, that's perfect. Yeah, that's a perfect example. Yeah. And the reason being that when you just multiply the two matrices, you end up with the same, right? Matrix multiplication. That's how it works, right? You multiply this matrix by this matrix, right? You end up getting D times K.
Yeah.
Right. Yeah. Yeah. Any questions? Anyone else has any questions? I know it's very mathematically heavy. I apologize, but without this, you know, as you can see, the reason why I have to introduce the math is because you need to know what exactly you're fine-tuning. You need to exactly know what numbers you're putting inside here, right? In order for it to work. So I have no choice but to go through the math of it. Yeah. Any questions before I move on to the next one?
You know what kind of data sets are like more suitable for LoRa, or some other data sets are more suitable for other fine-tuning methods?
So from what I understand, but from what I've seen, LoRa and IA3, which is the next one I'll be going through, is more preferable for very large data sets. At least in the paper, I mean, yeah, and whilst the first three, they're more preferable for when you have very limited data settings, right? But that's you know, at this point, we don't really know the answer to that. The reason being that, you know, it's new, not many people have tried it. And like I just, you know, we were just like Professor An, and myself, we were just saying, right? Unfortunately, when they introduce this concept, they're only going to advertise, you know, when you publish a paper with one of these innovations, right? And it doesn't perform well in a certain scenario, you're not going to say, hey, you know, it doesn't perform well, right? Yeah, you know, unless the reviewers ask for it. But you know, so unfortunately, yeah, it's up in the air. But from what I understand, or from just intuition, right? Prefix tuning, prompt tuning, and P tuning are more meant to exploit the few shot context of large language models. It's why they have that, the prompts at the front and the virtual invisible tokens at the front. Whereas LoRa and IA3, right? Because LoRa and IA3 are two totally different concepts, right? They are meant to exploit large data sets or large or language models which are very large, right? Where you would require a lot of resources, but these simple tricks can effectively fine-tune your model without using all the weights. So that's more intuition, but don't quote me on that. But yeah, I guess the short answer is that, well, that's why we're here, right? So we can perform experiments ourselves and we know, right?
Yeah,
right. That's why we do a PhD, right? Yeah. But yeah. All right. Any more other questions? All right, none. All right. I apologize. I know it's very math heavy, but yeah. So I'll go through the final one, which is IA3. So IA3, the first thing it's a follow-up of LoRa, right? And if you read the IA3 paper, they keep on referencing LoRa. But basically it's a follow-up of LoRa. So firstly, right, they introduced two new losses, right? The unlikelihood loss, and this is usually more for like rank when your task includes ranking and stuff like that, then you have an unlikelihood loss. But they first introduced unlikelihood loss, right, to punish the model, right? If an answer which is supposed to be of low rank is chosen as a higher rank, right? So therefore the unlikelihood is higher. So essentially it's just the reverse of likelihood loss, right? They have. And they also introduced the idea of length normalized loss. The reason being is that because, especially for autoregressive models like GPT, right? Your output is basically a product, a function of products, right? It's a product of a product, right? So as we know, you cannot have a probability of more than one, right? So, if you have a longer length, right, as an input and as an input, right, it is more likely to actually affect, or it's more likely to give you a smaller probability of the outputs, right? So to kind of counterbalance this, right, they introduce length normalized loss, and essentially it's just a sigmoid probability, right, exponential function of the original loss to that of all the combined losses of the entire length in itself, right? And they take the log of it, right? So this is just a probability, right? Because it's the sum of it with your loss, and then they just take the log of it. So they basically introduce two new losses first, right? And so this has nothing related to do with parameter efficient fine-tuning, but just bear in mind that these two losses may be the reason why it performs well, not necessarily parameter efficient fine-tuning. So now they introduce IA3, which means it's a fuse adapter by inhibiting and amplifying inner activations, right? So what they do is they introduce three new learned vectors, right? So like I said, the first one, so these are the first two, right? You have two learned vectors here, right? You multiply it by the value, right? The value and the key, right? So like I said earlier, right, in the activation function, in the attention mechanism of any transformer-based large language models, you have value, key, and query, right? And you basically take this, right? Take this equation. I know it's wrong, but you take this equation and you multiply it by the tokens in itself or the text in itself, right? To assign attention to the text, right? Like I love pepperoni on my pizzas, right? Pepperoni is referencing pizza, so therefore pepperoni, and when you compare pepperoni with pizza, they should have high attention values, right? And so basically this is the formula to get the attention values, right? So what they basically do is they multiply, they keep everything frozen, right? But what they do is they introduce these two parameters here, right? And it's initialized to 1. These parameters are initialized to 1, right? So these two parameters, the reason why it's initialized to 1 is simply because assuming there's no change, 1 would basically make it the same, right? So it's initialized to 1, right? It performs element-wise dot product, right, of the values and the keys, right? And these just by having these two parameters, right, you essentially could right, change, you could change the weights without going into the weights and actually touching the weights, right? By just having two element-wise products, you basically, the element-wise products tells the large language model, right, how much it needs to change, right? And the idea being that by having these two in itself, right, you keep the V. So in normal fine-tuning, right, you have to keep on changing the V and the K, right, and the Q as well. But now with this, you're just introducing these two learned vectors. They are initialized to 1, which means that at the very start there will be no change, right? And then you're just basically telling it now. You keep on fine-tuning these two, and you're telling them how much it needs to change, right? And the same as well goes. So after this, right, this is basically on top of this, but now you also introduce the same concept here, right? Between the non-linear activation function, and so basically right after the attention mechanism and the residual connections, right, you introduce this idea, right, before it gets normalized, and you predict the outputs in itself, right? You introduce the same learn vector here, right, at the feed forward function. Right?
So Charles, if you could go back to slides, yeah. So this slide, so you try to optimize the values for LK and LV that are two scalars, right? There are two scalars multiplied by the key vector and the value vector. So it means that because they are scalars, so you are scaling the key vector and the value vector by the same value. So basically, what changes is really the relative weights between the key vector and the value vector. Is that right?
Oh no, these are not scalars. They are matrices which are the same, which take the same dimensions.
Oh, same dimension. Oh, I see that. Right. You're right. Yeah, because it's dot product. Right. Okay. So that makes sense. Okay. So yes. Otherwise, I see. Well, it's only changed the scaling, but really not the attention. But now it changes the attention weights. Okay. Great.
Yeah. So this, it performs an element-wise product. So yeah, it's basically, it takes the same dimension as the key and the values. Yep. And
okay.
Same for here.
Great.
Yeah.
Great.
Same for here. Yeah. So basically now, right, depending on what model architecture you use, right, you could now see, right, you basically, L is the number of layers, right? You basically have 3 L's, right? From the, and if you take an encoder, like BERT model, right? You take an encoder-like model, like BERT, you basically have 3 L's, right? Instead of having to fine-tune everything, you basically now have to fine-tune 3 L's of matrices. And same for the decoder. If it's encoder decoder, right, like BART or like T5, the reason why there's 2 here is because there is an additional one that you have to connect from your encoder to your decoder in itself, right? So you have 5 L's. L's is the number of layers you have, right? So yeah, it significantly decreases. But what makes IA3, I wouldn't say perfect, but what the whole buzz behind IA3 is that IA3 is actually the first to show that they actually, across every single benchmark data set, when I mean every single, that means the ones that they specifically chose, okay? I'm pretty sure that there are some that they did not beat, but at least they claim the ones that, the ones that they specifically chose, right? They perform better than the fine-tuning threshold, right? And you can see LoRa is not far behind, right? And they also claim that they could perform better than the human baseline models in itself, right? And as you can see here, right, they showed that T-View here is the model that they used, right? T0, as you can see, right, it also is a lot cheaper and it consumes much less memory, right, compared to when you prompt the model once you have tuned it, right? So now let's go through this. Okay, I'm gonna kind of restart, right? So okay. So now I'm gonna go through them. All right. So again, the same, right? You just remember to load IA3 in PEFT itself, right? Read the data set in itself, prepare the data, right? and then you prepare the prefix. Sorry, it's not prefix. It's the parameter efficient tuning configurations. The good thing about IE3 is that you don't have to choose anything, right? So you just you just tell them this is IE3, this is my task type, it's a classification, and then you're done, right? Because like I said, that you know, LV is the same dimensions as V, and LV is the same dimensions as K. So, and they already chose the architecture for you, so you don't have to choose anything, right? And then you just initialize them. And then again, right, you are training only 0.5% of the parameters, right, compared to all the parameters in itself, right? You define the optimizer, and then now we just fine tune, right? And again, just within a few seconds. So you see, we're already reaching 79% for the validation. $81, $82, okay. So, all right, so, wow, 85%. You see, we reached 85%. So this has performed the best so far. But yeah, you can see we managed to do it all within a few seconds. In a very with reasonable computational resources. So any questions for IE3?
This is great. So Charles, you saved the best for the last, right?
Yeah.
So not only you're a great scientist, but also a good salesperson. Reserve the best to the very last. But
Yeah.
this is fantastic. So yeah, any questions, audience? Okay, so is this the audio presentation?
Yeah, so that's all I have. Yeah, that's all.
Okay, that's really fantastic. I personally learned a lot from it. I didn't know much about the parameter efficient tuning before I listened to your presentation, but really opened my eyes. Because if we could do this at a less than 1% of computational power compared to full length fine tuning, I would encourage us to use this all the time. I really, because we are not really trying to design the very best model in this world. We are trying to apply the model and with a reasonably good performance. So in this case, I would say the parameter efficient fine tunings are the way to make the model training much more efficient. And so we can afford experimenting with many different settings. A very easy extension of all the 5, 6 different fine tuning methodologies is to design a ensemble method, incorporating all the models. And hopefully, the ensemble is going to provide state-of-the-art performances, because each model, each fine tuning method has its pros and cons, and the predictions are relatively independent. So based on that assumption, then if you ensemble, basically combine those 5 or 6 models together, you may achieve a better performance even compared to the full range, full-fledged fine tuning method. You can try that, right? So that would be a great exercise for you, building ensemble of different parameter efficient fine tuning. Maybe you use 5% of the entire data, but still that is very fast compared to the traditional fine tuning methods, and you can achieve state-of-the-art results, right? So I would really encourage you to do that as an exercise. But I don't know for the others, but I feel really enlightened by this methodology, this set of methodologies. And thanks to the Python library, it made those methods so accessible to each and every one of us. So we use the same. I saw that you use the same package, just different options to choose different efficient fine tuning method. So really, really interesting. So thank you, Charles, for taking the time. I know you spend a lot of time. Your presentation is easy taking, but I know underlying you've made a lot of efforts reading those papers. There are a lot of technical details and implementation details behind the scene. So I would not say that the task is easy. I would say it's pretty hard and challenging, but your presentation seems to be easy to everyone of us. So I would encourage everyone, our audience, to try state-of-art methodologies and do a lot of experiment, because the landscaping of AI is just changing so rapidly. Right? So for the we will meet in 2 weeks, and so the next Saturday would be the last meeting in this semester, and then we are going to wrap up. We are going to celebrate the New Year holiday, and we will convene again during the new semester, the spring 2024. So in the last presentation, Yu is going to take the lead and talk about using AI as a tool for personal tutoring. So I gave her this idea as of today, and I asked her to explore it a bit, because given the vector databases, for example, the GPT-S allow you to customize the GPT model, and of course, other vector databases that are available to you, such as PyTorch. It opens up the opportunity for us to embed substantive knowledge into those large language models, so that we can make inquiries to the model, and the model can feed back to us using the ground truth knowledge and customize the knowledge to tutor us. Okay, so this is a feedback loop. We provide the data to the model, and the model feedback as useful information for us to learn. I don't know to what capacity we could do this, and it is a challenging task for sure for Yu, but I think it's really worth doing it, because if we are successful, even though half successful, we will be able to explore the vast potential of using large language models for personal tutor. Consider how much you have to pay Charles to be your personal data science tutor, right? So now, if we can use large language models, so every one of us can have a personal tutor that is trustworthy, that is based on grounded on truth rather than hallucination, and it really opened new doors and new windows and new insights for every one of us. Okay? So that is the reason why I encourage Yu to dig a little more into that. Okay. Okay, so that's all we want to cover for this session. Any questions, any comments before we enter this meeting? Okay, if none, I'll see all of you in 2 weeks. Stay tuned, and we will send an announcement later on. Thank you, Charles, for your contribution. See you, everyone. Bye.